Professional streamer here.
Huh?
Hey, hello everybody.
Hello.
I forgot to tweet, so give me 1 second. Let me tweet really fast. Okay, there we go. Cool. Hello everybody. Hello.
Hello.
So we're back with episode 2 of Type Theory Tuesdays.
Tuesday's type theory.
No, Type Theory Tuesdays.
Tuesday's type theory.
And look there. It's written right here. Just look here.
What?
Right there. Can't you see? It's right next to your face. Yeah. So yeah, it's Type Theory Tuesday, part 2. Just 2. Okay. And I've been working on the parser, like on and off stream. Yeah, I did my homework.
Okay.
So we finally have a parser, thanks to, well, also partly thanks to Christoph. He's been helping me at least yesterday.
Okay, recap. What are we doing?
So we're doing a lambda, well, a simply typed lambda calculus in Purescript. And right now we've written the AST, like the syntax, but in Purescript. And now we're trying to, and we've done the parser. And I'm going to show you what I've done in the meanwhile, like how the parser works and so on.
And what's the long-term goal?
The long-term goal. Thank you very much for asking. So the long-term goal is to, which of the long-term goals? Like the short long-term goal or the long-term goal?
Short
long-term goal. Okay, so the short long-term goal is to get this lambda calculus to be able to find terms automatically, which essentially translates to finding proofs in the.
How are we
Okay.
Wait. How are you going to do this?
Well, you're going to help me with that because you're an expert in logic, right? So we're going to use the Curry-Hall correspondence to go from lambda calculus or type theory to logic, and then we're going to use logic.
What ingredient from logic are you going to use?
Wait. We're going to use logical algorithms, like algorithm in logic and mathematical logic, to find proofs, and we'll specifically use sequence calculi.
Yay!
Okay.
Eh?
Do I pass?
Almost. Okay.
I don't pass?
9 out of 10.
Okay, so I pass.
Pass.
Cool.
Cool.
Okay, so let me show you our
the
current
homework.
parser. Okay, so let me show you the changes or the highlights. So I changed the syntax.
Did you ask me?
No. But I changed it to this because I realized we'll have a lot of trouble if we
With
don't
what?
do this.
So
like each abstraction will be a single abstraction. Right, we won't be able to do multiple at once, right? But you can still do like lambda x, dot lambda y, dot lambda z.
But you cannot write lambda x, y, z.
Yeah, and later, if we want, we can make the language nicer with syntax sugar, which desugars to this. But I don't want to do that, to deal with that now, because I think it will make our algorithms more complicated needlessly and so on, right?
I think also in the logic part.
Yeah, exactly.
It will create problems, so I think. Yeah.
Okay, yeah, I
Good
agree.
job. Good job.
I also thought that in the interpreter it will create problems.
Okay.
Not necessarily, but we'll have to deal with things which are not very recursively pretty if we do that.
Okay.
And I think the algorithm will be simpler like this. And then later we can improve them, right?
Application.
So I think that's the only change I've done to the syntax.
Let's recall the syntax maybe.
Sure.
My memory
So okay.
I'm getting old.
So
we have
let's start with terms, right?
Let's start with symbol.
With terms, why?
Symbol.
What do you mean symbol? You mean this thing or what?
Yeah.
Well, no.
Okay.
So this is a variable, not a symbol, right? So
Okay.
it's a variable, and
Okay.
when I want to store a variable, I need to remember the symbol, which is like the variable name, essentially, right? So that's what this means, right? So we can write x, we can write y, we can write z, whatever, right? These are all examples of terms.
Okay, and do you have any restriction? Like, can I start
They
with
all-
a capital A?
They have to be lowercase,
Okay.
or at least, first letter has to be lowercase, just the first.
Letter.
Yeah, and it has to be a letter. And then you can also have like apostrophes like primes, you have numbers, but not the first letter. First has to be a lowercase letter. First character.
Do you need to have 2 screens there?
Well, they don't see that, so I don't need it, but I usually have it like so. Right. So, okay, so then we have abstraction, right, which is pretty much the core of lambda calculus.
Yep.
right? You're able to create a, well, it's kind of awkward. You can't really, it's an abstraction, right? People can think of them as functions or as like any sort of other like construct, but it's kind of, if you call it function, it's not really a function because like it doesn't have a domain, doesn't have a codomain, like it doesn't come with all the baggage. But it's theoretically it's close to the concept, but not actually the same thing.
Okay.
And for an abstraction, we need what? Well, we need the lambda head is what we call it, which is this part, which is also a symbol.
Okay.
Then we need the term, right? So this is recursive. Like on the right hand side, you can have a variable, you can have another abstraction. For example, you can do lambda x dot lambda y dot x, for example, and so on, right?
And as you said, you cannot have a list of.
Yeah, and then later, so later you might add syntactic sugar for lambda x y to be the same as the previous one, right?
Okay.
For example, this, but not now.
Okay.
Okay, and then we need application, right? Because you need to be able to do something with your abstraction, right? Otherwise, you just create abstractions and you can never use them. I think that's application where you just put two terms next to each other, right? So it's, and usually the left-hand side will be an abstraction because otherwise you won't be able to do anything reasonable. But it's like you can easily just write this, and it's just that's it. You cannot do anything. But if you do like, for example, lambda x dot x and then y, for example, then this is something that you can evaluate to y. But we'll see that today, right?
Question: do you need to put parentheses?
Yes, because otherwise you cannot differentiate between this and the one above. Or rather, you cannot differentiate between x, this, where like between, this thing, right? Yeah. Like there's no way to tell, and by default it will parse it like this, right? So the lambda term is greedy. It will parse as much as it can.
If we don't put parentheses, it will.
As the right hand side, as this right part, right? So we need to do it like this.
Cool.
Okay. And then so these have changed since I last.
Okay, so we have left, right.
Okay, so we have left, right, and either, which kind of go together. But the thing is, these are terms, but these are like language-specific terms.
So these are some types.
Yes, these are for some types, right?
Okay.
Well, the idea is left and right, so they are all like just a unit constructor, right? They don't have anything extra, and the idea is how they will be used is something like you can write left, and x, right? But this will be an application of the left primitive with the x term.
But shouldn't you write application left x?
Oh no, application is just, well, okay, you can write this in our language, and then this in our term becomes an application of left and variable symbol x, right, in our language. Okay,
maybe we should look at some examples after
we'll do that in a second, right? Okay. So all of these are similar.
So you have just key
keywords. Because if I did this, then this would be some sort of special type of application where you can only do this, right? But then what if this is a function? What if, like, for example, what if, so either usually has a type like A goes to C, and then B goes to C, and then you have an either AB, and then you get a C back, right? But what if C is a function?
Okay.
Right, because you can evaluate a value to a function. Nothing is stopping you, right? You can evaluate A to a function, and so C could itself be D to E or whatever, right?
Okay.
And then it will be very hard to parse this, right? You kind of like you get into a lot of trouble. So then you did
pretty good your homework.
Yeah, I thought about things, right?
Okay.
So yes, so I figured it would be a lot easier to just treat these as keywords, and that's it. But they're like any term, a keyword term, right?
Okay.
And that's it. Okay, so these are the.
Have for products.
So that's the terms, right? And that's all we have. Then up here we have types, right? So what's a type? Well, a type could be something like T, or A, or B, or
capital.
Yeah, so capital, or ABC, or ABC, or anything like that, right? So, but it, like, again, same rule. It has to start with a capital, like an uppercase letter.
Okay.
Right. Okay, and then the second part, the function, right? So functions are types like this: a goes to b, a goes to b goes to c, and note that this is actually the same as a goes to b goes to c.
Okay.
As it parses,
If
right?
you don't add
If you don't parenthesize, these two things are the same.
Okay.
Right?
Cool.
Okay. And then we have sometimes, so you can go a plus b plus c, and again, this is the same as a plus b plus c, like this. Right? So I just hello, Christoph.
Hi, Chris.
Welcome. So sometimes like all of them actually associate like the same, right? To the right, I think is what it's called, right? Let's do the lazy replacement, right?
Okay, let's look at some examples.
And I think that's pretty much okay. Wait, no, let me finish. So
Sorry.
okay, so then so these are just like primitives, but they don't compose our, like, they are kind of primitives in our language. So how does a like compilation unit or a file or whatever you want to call, right? Like multiple things, like how does the language actually look, right? Okay, so we can do a type declaration, right? Which for now just introduces type names, right? So we're just declaring, okay, hello Bolt. So you can write type A or type B or whatever. So symbol is just a string.
Up a bit,
Okay, where? So we're not using this yet, right? There.
Okay.
Symbol is just a string, right? So here we're just saying, okay, this string represents a type. So this is just to make sure, like, we
so
don't.
type declaration should be type.
Yeah. And then, okay, this is the important part, right? This is kind of, we don't even need this. We can just assume
so
they
okay,
exist.
you split
But
it. Okay, I see.
yeah.
Type declaration, type definition.
Term definition, right? And a term definition is, okay, we have a thing, this thing is actually has the same rules as variable names, the function names.
Okay.
Right, so it's still lowercase and so on, right? So you need like a variable name here.
Okay, I see what you
And then we give its type, right? By this syntax, we add this to like colon, and then we can put any type here, right? Like, yeah, so
And we will
the type that we
see
saw
if
above,
can
right?
be
Like
inhabited
this
or
one,
not.
right?
Okay.
And any of this, right? So, right?
And
Note that I'm pretty sure the way we want to do it is if we do g of type A here, we can do like g equals A. Do you want this to be true or no? I don't think so, right? We don't add axiom, so that cannot be, like, those can
For
never
the
be
moment,
implemented
no.
for now, right?
Yeah.
It's only like we can do identity, but we cannot do this one, right? Okay.
But we can
Later, we'll figure it out later.
next step.
We might add primitives like integers or
Okay.
booleans or whatever, and we'll see what happens.
so
But
then
for now, that's not the
Okay,
case.
please.
Okay, so this is the like signature part, and this is the implementation part, and then you say f equals 2, and then you define a term which is exactly any of these things that we've already seen.
Then when we move to the logic, we will be able to do at least two things. First, see if the definition of the type is inhabitable or not.
Which is the type, right? So
Which
we
is the
translate
type.
this type to a logical proposition.
And then we will
And then
see if that can be, it's a tautology or not.
Yeah.
And then the next step would be to populate
Find the proof.
populate the term by translating.
Well, it depends. Like, we could even start by doing a checker, right? Where we just check that whether this thing has the correct type, right? That might be simpler, because then maybe that's how we check a tautology, right? We check that.
Okay, but do we have to move to logic to answer this?
Not necessarily. We could just implement type theory if you want, or you could use the logic to just have like to dip our toes into.
Okay,
we'll see.
Okay, nice.
Right, and then the actual file is just a list of AST, right? You have a list of type definitions and term definitions, right? Like a file or a compilation unit, right? Because you can have multiple of them, right? You could have multiple.
Okay.
We could start by just having like multiple of this and just one of this, but later we would like to be able to say, okay, if.
But do you have any okay, so if you declare a function, then you also have to put your implementation, right?
Say that again.
Can you define, for example, f and then g, and then give the implementation of f and g?
So you mean use g inside f or the other way around?
No, I mean just right here g. I mean, after you declare a function, you must give the definition right underneath.
Oh, right. I mean, what if I do G here or what?
Yeah, exactly.
No. So,
Okay, so
that's an error.
That's an error.
We'll see in a second because I have a lot of tests for this sort of thing. Well, not a lot, but some. So Christoph asks, what's your induction forms for you? Okay, so the only user-defined types are voids for now. So no, you cannot create a type like a value. So for now, we consider them just propositions. They don't have any structure. And so, for example, you can never write f of type A, but you can always write f of type A to A. I keep using that, right? So for now, we're only looking for tautologies, right? For things that are provable without any other axiom.
Yeah.
And then later we'll figure out, we'll add maybe at least some types. So we can do like true or false or something for bools, because that's pretty easy. And then once we do that, then we'll probably think about integers, but that's more complicated because if we want them to be infinite and so on, we'll see. Yeah. I mean, we could define integers by piano and then it would be easy, right? But we'll see. Yeah. But anyway, for now we want just to do the simple thing where like we have types, and I'm not even sure if we need to declare them. We might just assume that any type you write there is already declared or something. We'll see.
I think it will be easier if you declare the type as
for later, right? It will be like when we add constructors.
We will use them as not necessarily. I'm thinking from the logical point of view. You will use them as propositional variables. Otherwise, we have to define and count set of proposition variables.
Okay. So then we have the parser. Which I will not even go through. Yeah, I will not even go through this because the code doesn't matter. If you're interested, you can go to GitHub. I'll give you the link in a second and you can read it. We won't go to the code. I'll just show you the test, which also have a lot of examples. Okay, so here's just some helper functions. Ignore them. So here's the test, right? So variables, these are so positive inputs. So, this is the name. This is the parser used. And this is positive input, so we expect all of this to pass. Hello, Vince, welcome. And we expect all of this to fail as variables. And for example, the reason this fails is because it's a keyword, right? The reason this fails is because it starts with a 1. This is an empty. You cannot have a space as a variable. Space is, you cannot have an uppercase character, right? But all of this pass, for example, right? And then this like specific data is, I want this to pass, but I want A1 to specifically parse as a variable A1.
Was that parsed?
Here, right? Yeah. So this means that, because for example, if the parser was wrong, it could parse A as a variable and then leave 1 as unparsed. And I had that bug at some point, right? So I fixed the code, but then I added this test which makes sure that, if A1 parses, it will parse as a variable called A1. Right, and then like primes also work, and you can also have, I think the music should be stopped. It's, mic volume is low. Let me try to boost it up a bit. Let's see. That's the wrong button. Let us know if it's better now. We'll try to talk a bit louder.
Testing.
We should also try to talk more into the mic, right? Let's get code here. So it's because you're both. I'm sorry. We'll get more.
Come on, it's cold outside, so.
You can have like apostrophes in the middle. That's totally fine. You can have underscores in the at the end, in the middle, whatever. You can't have Greek letters. I'm sorry yet. I'll figure it out later.
It's fine.
It's I left it here specifically so I remember to do it later. But and then any keywords. So keywords are these things, right? The left, second, either left, right, either tuple, first and second. And then whatever, right? You can these are the only ones that work. Not very interesting here. Then abstractions, right? We have to escape backslash like in all other programming languages. So, but in our source file, we only need 1, right, in the text. But as strings in the language, you need to use double backslashes. And then, why does this work? So this works because it's a single. It's a single variable xy, right? There's not 2 of them. This you cannot have double backslash. You cannot have 2 of them without a dot here. Well, actually, let me fix this test because this was a test that was just meant to test that you're meeting the dot. And then this is wrong because it's missing the dot here, right? After x. Okay, and then I've also tested that this works and you don't need parentheses. And this means this parenthesis, this, right? So it's an abstraction of A, an abstraction of B, an abstraction of C, and the result is A.
Okay.
Right? Okay. Then application, again, we have X. You can put as many things, you can parenthesize them however you want, but normally if you don't parenthesize, then you get X, you apply X to Y, and then the result is applied to Z, right? So it's left to right.
Okay.
Right, so you do these two first and then the result to this. As you'd expect in a in lambda calculus. Okay, so then these are all like specific, just this part of the term, and this is the whole term where we have examples that are a bit more complicated. So for example, you got lambda in the left here, or a tuple here, or whatever, left and application and like parentheses and so on, and we have a few examples here. Not a lot, but I'm fairly confident that it works reasonably. And we'll see. If we find bugs, then we'll add more tests.
Okay.
To make sure it works fine. Okay, and these are the tests for types, right? So these are all acceptable type names. These are not because they don't start with an uppercase letter.
Okay.
These are all functions, and you can parenthesize them, right? And then this is an example which shows that this translates to a function from A to a function BC, right? Because that's very important to be parsed correctly. And I have the same test for all of them, right? So all of them parse in the same way, right? It's a sum from A to BC, to a sum of BC, right? And here again, another some examples here, like wrong syntax, where you're not having a right-hand side, or you have like dots or like weird syntax and so on, right? Same for multiplication. And then for types, we have some tests. Okay, so I've done this, like there's some priority here between these three. That was Christoph's.
Okay.
He told me how to do it. So in this case, for example, multiplication binds stronger than addition, like in numbers,
like in arithmetics.
Right? Like in arithmetic, right? So this is a sum of this product and this, right? So it's a sum of A times B and C.
Okay.
And this, this binds least strong, basically, right? So, because that's how you expect, right? You'd expect the product of A and B to go to C, and that's the most usual thing that you will write, correct? So this is a function from A times B to C. And again, here is a function from this function A to B, and goes to the function C plus D, right?
That's not the function.
To the sum C plus D. Right, and then we have the AST parser, which parses like a single instruction, right? So it can parse type A, type B, or type ABC, but not like type underscore, not some garbage before type, and not, you cannot do this thing, right? Where you, like here it has to be literally just a type name. And then some example of definition here, for example, f of type A, and then this is a new line. And then f is a lambda, whatever. Again, this doesn't type check, right? So you can write anything as long as the syntax is correct.
Yeah.
Then I wrote identity here and like a few functions, but they all seem to pass. These are negative inputs. So for example, this doesn't have a body, it just has a type. This one doesn't have a type, right? No type declaration. This one is defining f but trying to implement g.
Okay.
Yeah, exactly. So we actually had it. And this is the same, the same problem here. So, well, actually, okay. So this tries to declare two things at the same time, and then this tries to like implement something else.
Okay.
And here's the what is this? What's the difference between these two things? Okay. So these are single instruction, I think. I have a very serious question. Have you named the language? No. Do you have a? It's called lambda calculus for now, but
we have to have a name.
You know that I have a Haskell bot that's called HaskMeBot, and that's Vince's idea.
Okay.
So I wonder if you have a suggestion, Vince. Okay, so let's see. There's another few. So this can only parse term definitions, right? And then this thing can parse either, right? So it's kind of this or this, right? So that's why we have examples of all of these things. And then I think we have the file parser, which just parses multiple of this. right?
Okay.
So for example, it can parse just a single one, of course, but it can parse like it ignores comments. You can have new lines. You can have as many like new lines here or here or here, and it should still result to the same thing, right? Which is like it should still parse the same thing. Then here we have some examples where we actually test that the thing works. For example, this is a more complicated example where we're parsing an array where we have the type declaration A and B and the term definition for F, which is a function from A to A, and then it's a abstraction from X to X. So we have a parser.
Cool. Yeah.
We can parse things. Cool. So now we want to interpret them, right?
Yeah.
I remembered.
Yay!
Oh, and also let me show you. So, are you ready? Look at this pretty thing.
Is it going to woof?
So no, it doesn't woof anymore. Look at how nice it is, because it tells you that there's paths. Look at them, like they're nice, like. And then if I do something wrong here, the error is actually reasonable. It's not oof.
Not
anymore. No, I'm sorry. We're done with oof, right? So the failed parser failed because we were expecting this, and where is it? We're expecting this, but we got this, right? Not very easy to read. We need a pretty printer to make this easy to like.
It's fine. It's fine.
But for now we can.
It's fine.
This is
good.
readable.
It's good.
Well, I mean not readable, but at least you can figure it out, right? So we can find the errors. So we have tasks. So now we want to do, okay, let me, because I did a couple of minor changes, so let's do a commit and let's say parsing done for now. Okay, so let me quickly the calculus. Okay, let me share the link in chat if anybody is curious and wants to have a look. I just pushed this, right? So if you want to follow along, you're exactly up to date. Okay,
what's next?
So right now I want to do the interpreter.
Okay.
Right? What? Hang on. I think I interpreter.parse. Okay, where's the file? What am I doing? What's happening? Okay, so let's try that again.
Take 2 minutes.
Why doesn't it add the file?
Until you figure out how you
help!
The
Why
file,
doesn't it add the file? Oh, it created a folder with that name. Okay. Wonder why. Oh, I think I know. I think I accidentally pressed backspace the first time. Okay, so now it worked. Okay, so the basic idea here is that we want to be able to, so what can you do? Because we can't really like interpret in a real sense, right? We can simplify. So maybe we should call it simplifier then. Yeah, I think that makes more sense. So the main thing here, like this is pretty trivial, right? We need a simplify function which goes from lambda calculus, which one? I guess it needs to go from a term, right? I'd given a term, we just want back some term. No, I mean, okay, it's not trivial to write necessarily. It's trivial as in the function is very simple, right? That's all you need to do, right? You need to simplify a term. Now, whether the implementation is as simple, we'll see about that. Where is prelude? And we're done. But no, seriously, we need to like this is the thing that we need to implement, right? But obviously the identity is not the correct implementation. And here we, don't you need something like list AST to ST? Maybe. Assuming that we use functions from from the AST, right? We use, yeah. So do we want to allow people, welcome back.
Sorry.
So do we want to allow something like, so let me show an example here, because we have this thing which, why is everything commented out? Oh, okay, whatever. Let's just delete it because we have most of those as tests. So do you want? So let me write an example here. So let's say I have A to A and then F equals like this, right? So this is, so far this is correct syntax. We're good, right? So let's say I want to write G. Can I do this? Do you want to allow this or not for now? Is the question. Or we can even do this, right? And we can say whatever, just so it's not identical.
I mean, I think from moving to the logic, it will not affect us. So
you don't care.
I don't care. Exactly.
I mean, as a programmer, it kind of feels like we should, right? Because then, like, you kind of need to be able to reuse things, right? To write simple things and then reuse them later, and to also make it easier for us to write more complicated programs, right? G equals FF. Yep. So yeah. Okay. So we want to do this, right?
Yep.
We want to be able to do that. Okay.
But does it pass that test for the moment?
Yes, because f is a lowercase, it's just like a variable, right? And it doesn't check variables, right? Okay. So it will be, so that would be the unbounded variables will be, can only be other functions in the same module, basically, right? Or an error, right? Because you can definitely type, where is it? Like I can do here h of type A to A, h equals to A, right? This will parse.
Okay.
But that's obviously an error.
Mm-hmm.
Like we can't do anything to this. Or we could just like not change it, right? Because, okay, so what I was saying earlier is like we're not really writing an interpreter, we're kind of writing a simplifier actually, right?
Yeah.
Or evaluator simplifier, something like that, right? I named it simplifier. And they're saying, okay, the main function is term to term, but actually we want, Christoph is right. We kind of want list AST to well, no. So I think what we want is an array AST to, and wait, is array? I think array is primitive. So
wait, you want to simplify each term as much as possible, or find out if...
So I think we want to simplify a single term, but you need an array of AST as your environment, right? You want to know all the other things in the module.
Okay, like you had the example with...
Yeah, so now we need F and like all the other things, right? And this is kind of like the environment you're working in, right? The array AST. And then the result should also be a term, right? Because you're simplifying a single term, but you need to know the context, its context, right? The rest of the module, which is the list of AST.
Okay, let's see.
I think. And like the thing you're currently simplifying, you don't need to know, since we're not doing recursion, we don't need to know its name, right? Well, we might need to know its type, probably. No, we don't. We don't care about its type because we're not type checking, right? Because like an AST, right? So what can we do, right? So we can simplify only a term definition, correct?
Yep.
And if we were doing recursion, we need to know its name, right? To know if it calls itself. But we're not doing recursion, so we don't care about its own name, right?
Mm-hmm.
And then we look at type. We don't care about the type because we are not type checking. We're just simplifying, right?
Yeah.
So then we only need its term, right? So, I mean, sure, I just solved the first two arguments. Probably. It depends, right? If we end up using reader, okay, yeah, maybe we can just do this. Okay, and then it's no longer identity. We can do this instead to fix it for now. Okay. So I guess let's do something. So let's make it such that it's. Although I said we need to look at this, let's ignore this for now. Let's just keep it there, but let's not look at that for now, right? Let's do the simple thing where we let's see if we can simplify identity applied to some constant or whatever, right? So I guess like what can you do? Well, you can pattern match, right? That's the only thing we can do here, correct? So let's actually let me open the syntax on the other side, just so it's easier for us to see, right?
Yeah.
Okay, so let's say if we have a variable, right? So if we're trying to simplify a variable, well, we can never simplify a variable, right? So that's just, so if we get a variable x, wait, can Purescript do x at, can we do that in Purescript? I don't remember. Does this compile? Well, it doesn't know what variable is. Let's do, okay, let me do something else. Import this as s, and then let me just add s everywhere. Okay, and the problem is it doesn't have the other case expressions. Okay, can we, unfortunately you can't. Okay, so then, okay, what do we do if we have an abstraction? So we have an abstraction, right? That's the point where you look stuff off in the environment in the future. Okay, so let's see. If we have an abstraction, right? If we have an abstraction, then we have a symbol, right? And a subterm, right? So most likely you want to simplify the subterm, right? But then you probably also need to do something, right? Here. Like we have to somehow, well, let's not worry about that, right? So we obviously need to simplify the subterm, but we kind of, I guess we need to also, we cannot destroy the structure, right? So we need to keep this, right? But we need to simplify the subterm.
You have a symbol.
Symbol. I'm pretty sure, right? Something like this, but then we might need to like pass some info to simplify, but we'll see later, right? Because we don't need it right now. So let's look at application then. Where we have an application between some term and some other term, right? And here's the thing. I think we need to differentiate between types of application, right? Because there's only one type of application where we can actually do something, and that's where we have an abstraction on the left-hand side, right?
Okay.
If we don't have an abstraction on the left-hand side, then we cannot do anything, right? So I think we need to further pattern match here.
Wait, can't you simplify on the left? I mean, if you have two terms, maybe you have to simplify both of them.
Well, I mean, so you mean simplify left and simplify right, or what? If you evaluate only two weak head normal form, you then move under the binder for evaluation. Yeah, but we don't do weak head normal form, right? We kind of want to evaluate everything. I'm pretty sure. So, okay, sure, you need to simplify left and right as well. Oh, so you're saying simplify left first and then see if it's an abstraction?
I think you have to simplify both of them.
So you're saying like you have left and right, and you're going to do something like case simplify right, left of. Sorry. Right, so in this case we need to like substitute symbol in left with right, I guess, or something like that, in simplify right. And we need to simplify the result. Do we? Yeah, I guess so. Something like this. And again, we don't have the substitute function. We'll have to figure it out. Right? Is that what we need to do? Right? Because like, let's write an example, right? So, wait, isn't this a? Huh?
Okay.
No, not okay. Why isn't this a comment? Whatever, we'll write comment like this. I think it actually is a comment, but again, I cannot complain about the plugin because I'm the maintainer of the plugin.
Well, maybe you should complain.
Right, so let's say we have a lambda x, let's do the simple thing, and the y here, right?
Yeah.
Well, actually, let's make an example where this simplification actually does something, right? So let's say we have this, and then let's do a b here, and then b. What?
Cannot have a b.
I mean, sure, we know what it means.
Okay,
syntactic sugar.
Sorry.
Okay, and then z here, whatever, right? Okay, so let's see. When we start this, we get into application, right? Because we have this and this, right? And this is left and this is right. Okay, so we simplify left, right? So we go back and we find another application, right? And then we try to simplify left, but there's nothing to simplify here, right? It just hits this and it doesn't do anything, right? It tries to simplify a, but again, that's a variable, so we get it back, right? Okay, and then we get this and this, right? So then what do we need to do? Well, we need to like remove this, right? This abstraction, and we call simplify on substituting the symbol, which is a. So we substitute a in left, which is what's left? Yeah, it's this, right? With the simplification of this, which again isn't. There's nothing to simplify, so it's just this, right? So then you just have like you end up with b a no by, right, after the substitution and z, right? So that seems reasonable, right? The tricky part will prove to be substitution, but we'll see about that. Right. So if we have an abstraction, we can do that, and otherwise. What else can we have? Do we need to? No, otherwise we have some term, right? Right, which could be a variable or something else. And I think the only thing we can sensibly do is just leave the application as is, but simplify it, right? So it's term, prime, so we've simplified the left-hand side, and then we just simplify right. Did I mistype?
No, I think it's fine.
Right, so that's all we can do. So I think that's everything except we need to amplify substitute. Oh, that's all we need to do.
That's all, yeah.
I mean, well, no, that's not all. We still have these things, right? We have to do something in this case. What do we do in this case? We do nothing, right? Like you cannot evaluate left of x. It's just left of x. Oh, I think we need. Hello, Radu. Oh, you know what? I think we need to evaluate. I think we need to evaluate either first and second.
Yeah, when they're combined, right? Do we simplify this? I mean, or if you have a projection of a tuple. If you have first of a tuple, do you simplify it? Okay,
let's not worry about that yet. Let's say that in any other case, we just return the term as is. And okay.
The red book?
No. Let me do
if you have like...
So I think the idea is that you simplify, like so you assume that this has at least one argument. You simplify it, right? Well, left cannot do anything, right? Because left just creates something.
If I have,
for example, first, if you have first, then you assume that it's like you take its first term, you simplify it, and then if it's tuple, you can they cancel each other out, and then you get the first argument of tuple. And then if after first you don't have a tuple, then you can't do anything and just stop. Just right. But that's a problem for later. Let's just deal with the simple lambda calculus first, right? Okay. And right now what happens is whenever we find this, we just stop. We don't simplify further, right? We don't know how to.
Okay.
Let's go substitute now. Because the thing is, I want to have this and I want to start writing tests.
Okay.
Right? And I want to see, okay, did we get application right and abstraction? Because if we did, then we will reuse those ideas here, of course, right? We just need to have some special cases. Okay, so we have what we have here. So we want a symbol, right? We have a symbol. Do you want me to enable it? Okay, let me know. Okay, so we have a symbol, a term, and a term, and we return a term, right? Right, because we're looking for this symbol,
and I replace it with that term
in this term.
Okay.
And we replace it with this, and the result is
Can you write on top
Well, I can write here a symbol, source and target, or what would be good names for you? Term and substitution. Is that reasonable?
Substituent. I don't know. Okay, just write sub or something. Okay.
Like this?
No.
I use replacement and term. Okay, replacement is a good one.
Okay.
Okay, cool. So, okay, let's do first version, because again, the first version is where we will not worry about, okay, so what can happen? What's the trick here? The problem here is that you could have something like lambda x dot lambda y dot x here, right?
And you replace with...
And if you replace with y, this y is not the same as this y here, right? So here, if you do that, then you should end up with lambda z dot y here, or whatever, like some name here, correct?
Yeah.
I think, right? That's the problem.
Yeah, because if you don't rename, you will get...
this becomes bound, right?
Right, and you will get lambda y, which is a different function,
right?
From what you want.
But for now, we will not worry about that.
So we assume that
the user has written reasonable lambdas.
So you assume that the replacement doesn't appear in the term.
And then there's a way to fix it, and if we have time, I'll fix it. Right, we don't deal with renaming at all. Okay, so what do we do? Well, again, the only thing we can do is, or the only thing that makes sense is to pattern match term, right?
I have maybe it will be easier to read if instead of symbol you would write variable.
What about name? Variable?
It's a variable, right?
Sure.
And also maybe it will help if you do the same in the definition of simplify.
Simplify.
Okay, let's go back. So you have an abstraction. So you have an abstraction of a variable and a term, and then you simplify the term and you... Okay. I'm mumbling. Yeah.
Yep, makes sense. Okay, so we can look at a term, right? So if we're trying to substitute... Okay, so if we have a variable... Hello.
Hi.
Hello, Alex. So if we have a variable var, right? And we're trying to substitute it with...
replacement.
well, okay, so the first thing is var the same as variable? If it is, then we replace it. If not, then we leave it as is, right?
Yeah.
So we can do this, right? So we can say variable is same as var. Then we do replacement. Otherwise, let's just do this, right? Oops. Okay. Okay, so that's the first case. Actually, is this valid syntax?
Yeah.
I don't think it is. I don't think you can have. Okay, is this valid syntax then? I think in Haskell it is, but apparently it's also in Purescript. Okay, I didn't know.
Okay, so replacement comes with variable.
Yeah. Okay. And then if we have an application here, right, of term, well, left and right, we just substitute in left and right, right? Left replacement. We need 2 lines for that. And right. Correct? We just go inside the, like, both ways. And then if yeah, that's correct.
And if you have anything else.
No, and then, well, like if we have in lambda, right?
Okay.
So if we have with a like some different variable here and some some term here. No, let's not use term. Let's log inner term, right? Then we do the same thing, right? As not abstraction, because like the inner term could also have the outer variable, right? It's kind of like here, right? Like if we're replacing here, then we need to look inside here to find this x, right, and replace it. So like we keep the same variable name here, right? We don't touch this, but this is where we would have to make sure that this isn't like doesn't clash with the term, right? This is actually where the tricky part is, and also probably in the replacement somehow, but I'm not sure. And then we need to simply substitute the original variable. You need to check that the binder doesn't shadow the scrutiny, otherwise you have to stop. I'm not sure what scrutiny is, but I think that's what we said we don't.
So we
bother
assume
with.
For the moment.
Yeah, we assume that they don't. Because I want to test simple cases, and then I write a test which breaks it, and then we can try to fix it, I guess. So we substitute variable in inner term by the same replacement. Why is it the last line here? So, wait. Otherwise, so if you want to replace, that's a different case. That's not capture. Oh, so you mean when you have const, when you don't have. But what would the problem be there? Because you'll not find any x in 4, which is the right hand side, and then you just don't care. So I don't see why that's a problem. Okay, you want to replace x by 4 in that. So wait, I don't see what the problem is in that case.
Because you should, I think you should. So the answer should be, yeah. You don't have to. So and you have to keep the identity.
Why? Don't I kill the lambda heads? Where? Here?
Yeah, but you shouldn't.
What do you mean I shouldn't? Like here we get rid of this, right, of the variable. Right, and the result is 4 in this case.
Yeah, but you should obtain lambda x dot x. You shouldn't replace that x.
No, I think this means that you have. Okay, so let me see if I understand your example correctly. Let me actually make this compile because it's annoying me. So if otherwise we just return term, I think. Okay, so your example is that if I have this and this, right?
Yes.
Like this is the initial example. And then, so if this is here, but here, right? this is where this starts, right? So we'll get into application, and we'll find that we have an abstraction on the left-hand side, right? And then the result is simplifying the substitution of variable in left, but left prime is this, is just x. So we're trying to substitute
and then
x with, and the result is 4. I don't think we end up with lambda 4. I'm pretty sure we end up with 4. Because like here we pattern match an abstraction, but we don't create an abstraction. We just create the left. Where we substitute the right with variable, but okay, let me look at that example. That's lambda x dot lambda x. Oh, okay, yeah, but we said that that's not allowed, or actually we accept that that's a problem for now. What's the problem here? Oh, okay, this is okay, so we need to actually pass this thing around for now. You know what? For now, let's just remove it for now, and then we'll add whatever we need later. Yeah, different problem for capture. Yeah, fair enough. So let's write some tests. Because I think it should work in simple cases right now. So let's say it's parser and then simplifier for tests. Okay, so let me copy some things over from here. Simplifier. Suit is test suit. Let me see, because I don't quite remember 100% how this works, so let me try to remember. Okay, so we have this thing like, okay, which we do simplifier do, and then here we do, I'll just add a few simplifier tests here, and then okay. So this is also test suit. Let's do batch 1. Okay, so let's write a manual test here, and then we'll see how we can make it reproducible. It's simplify, right? Okay, so we want to basically do simplify, right? So we want to call simplify, and we want to give it a term, right? So the term would be, but I don't want to actually do parsing here, right? So I'll write the term in like in our language, in Purescript, rather than as a string, because if we have a parsing problem, then I don't want to break these tests. So what's the simplest thing? Let's do like should we do like the ones that don't do anything? Like, should we add tests for this, or yeah, I guess we can add some, like a couple of tests for that. So we could say what? That we can simplify a variable, right? X, right? Or a variable Y, and we should get back the same thing, I guess.
Okay.
Okay, so let me see. Parser test. So what was the... Okay, so do we have something like, oops, cert dot equals? Why doesn't this? This doesn't seem to be compiling for whatever reason. Or is it assert t? Okay, there we go. Should equal. Okay. How did we end up doing the lists here? Did we... So I think we need something similar to this. let's just write it manually. So we should do something like should we call simplify of var x with var x, right? I think that's the test. And then of course we need to like give that, and it would be nice if these were okay. I'll just copy them for now, and later I will make a separate module, like a common module. Okay, so okay, I think we need to put them inside a test, right? So it should be like test variables do.
Okay, I was really struggling to understand what this small var is. Now I see.
Oh yeah, it's just like
okay.
a helper to make things easier. And I will not clear this up because we'll probably need some of those. So, but we definitely won't need the parser. But okay, so I think now if we go to main, I think it would actually be a good idea to use the parser here. I mean, it would be good from the readability of test perspective, but it's bad.
For our sanity.
It's bad for like if you get an error, you don't know if it's a parser error or a interpreter error. I think I prefer the like this way to like use similar syntax using helpers, but not quite the same. Okay. So let's see. Oh, it passed. Okay. I've tested it. Yeah, 100%
Formally verified.
Yep. Okay. So let's do abstraction, just to make sure it doesn't do silly things. Confirmation bias has no play in this. So let's see, we could create an ABS which takes a string and a term and gives us back a term. Var s, no, okay, it's sim s and then p. Something like that. So we could say something that if we do an abstraction x and var x, for example, right, we should get back the same thing. Okay, let's write a helper which tells us that we need identity, right? So it's a okay, so what type is this? This is a test. Okay, so careful with sim, you'll confuse the mathematicians with symmetry or what? So what's it called? Simplify nothing. We'll find a better name to this. Why? Parser? No, yeah. I refuse. I absolutely refuse. And then how do you test if they're equal? You still need to write the result as this in the end, right? Like you parse it, but then the result is a term. We can't unparse back to string, so it's going to be harder, right? The way I'll do it is you'll only write this once. So let me show you what I mean, and then
you can put simplify on the parser and the term, and then on the right you just put parser on the term. Right?
Oh, you need to like parsing it twice. Okay, yeah, you could do that. The people demanded. Okay, let me show you what I mean. So if you give me a term, I'll give you a test.
Then you can finish afterwards your homework and you can write it as this.
I think it will take more time to do that. Because right now, like if I have a term, I'll just do this. Right, where I just replace t here and t here.
But you destroy the beauty of your language.
What do you mean the beauty of my language?
I mean,
Okay, look at this. Isn't this pretty?
Very.
Okay. Let's do another abstraction. Y and this. I guess this should also pass. Yep. My eyes have never seen such beauty. See, Vince is on my side. Okay, let's do the interesting things now. So let's do identity, right? And then we need to apply. Yeah, I know, we need to apply this to var y, and then we should get y in the end.
Yeah, but it simplified nothing.
Yeah, I'll replace it.
Simplify something.
Simplifies to yeah, I don't know. It's a good thing you didn't catch my British sarcasm in that. Also, you were using scheme now. So term simp. Okay, so here we need to do something like oops. Simplify term return simp. Var y.
You sleep on the couch tonight.
Okay, we didn't do app. I'll do it, and I'll show you that it's worse.
What's up?
Okay. Yeah.
You really don't want to go into the logic part.
X. What's X? Oh. Why doesn't this work? Okay, there we go. Hello?
Even the computer refuses.
It worked. Okay, so you want to replace this with.
Now don't delete it. I mean,
I'm not gonna delete it, but like I'm okay. Okay, so you want to. I don't even know how to parse.
I think that was the problem.
Because you need to do what? Run parser. What's run parser? I think we need to copy. Well, huh? Okay, so we need to do something like case run parser of the parser for AST, because we're doing single AST, right? Or no, for terms, right? We're using terms. Okay, off, and if we get left error, we just do failure. And then if we succeed and have a term, term T, I think. Wait, what's the order? Run parser. Oh, input is the first, so it's input here. Okay, that's a bug in the plugin, I know. Okay.
What is term?
Okay, so this should be T. T is the term parser. That's the name of the parser. It parses terms.
Okay.
Then we should say that assert. Okay, this thing, right? Right?
Wait. Okay.
Then here we could say X like this, right? Here we could say unsafe crash with. yeah, I've never used that. So this is lambda x dot x, I guess, right?
Yeah.
And this is lambda y dot lambda x dot x.
Phew.
Okay, let's see if it compiles. Show. What? Cannot match string. Oh, okay, because we need to do this. Let's see if those pass, and then we'll change the others. Okay. Okay, so simplifies 2 also needs to be changed and to use something similar to this. But then we need to, okay, so yeah, we need to change these to strings, right? Okay.
Keep
the what? Sorry.
Simplify nothing. Do you need it?
You mean this one?
Yeah.
No. Sure. Okay. So this is the input.
In the name of symmetry, right? Simplifies to p or something.
No, I'll remove the p from the other one.
Okay.
And then this is the result. Actually, we don't need to do that. I've learned that we don't have to do that, and we can do this. So if we have, okay, let's do this happy path first. So write term, write expected, and they should, like, simplifying the term should be expected, right? The expected result. Then in all other cases, okay. And then here we're supposed to write that lambda x dot x in parentheses and y simplifies to y. Okay. No, wait. Huh? Oh, I removed that one. Okay, so I need to replace GP with G. Okay. Okay, so let's add a few more examples then. So lambda x dot lambda y, and then this will crash, so we need to do a here, right? But the result is not the same, right? So it's lambda y a.
Yeah.
Perfect. More examples. Hello, Yu-Gi-Oh. Okay, so let's see that it simplifies things that are, so for example, what if we have x here, so something that's unsimplifiable on our left hand side, but we have something like y, well, x dot x and z here, right? Like, I want to see that it simplifies the right hand side, and then it ends, like, the result should be xz, right? Okay. I think that's fine.
Do you have some exercises that you use when you're teaching?
Oh yeah, but I'm pretty sure they will fail.
Okay. Because of the substitution problem.
Probably. Because like a lot of
so
them.
we cannot parse this for the moment, right? What will happen with this example?
I don't know. Let's see. So you wrote x dot x, and you want to replace it with x dot x, right? You would expect to get back x dot x. What do you mean no?
Yeah. Okay.
Yeah, right. That's what you expect to get back? In this case it works. Okay.
When you have a non-terminating,
it will probably not terminate.
should we check this? What was the example? Yeah.
Right, this is the one. Pretty sure it will Stack Overflow.
Maximum. Okay.
Yeah. No, it doesn't. I don't think we want to do that. But I mean, that's good, right? It means it's omega fun. I mean, like stack call exceeded means that it definitely did the right thing, right?
Yeah.
But of course, this would not type check, so right, this would fail the type checker, so it will never reach simplification because you cannot. This doesn't have a proper type.
Okay.
We don't have a type checker, but if we had a type checker, it would fail it. So we would not simplify before type checking, of course.
Okay.
Okay, so this doesn't make sense. Okay, so what are the examples? Okay, so let's say so what are the things that we know don't work right now? So one example is, so if I have a lambda x dot lambda y dot x, right? And we pass it a y here, right?
Yep.
Because this should result in, like, we don't even know what it should result into,
yep.
Right? But it should not be y dot y, which is the case here,
yep.
Right? So this is bad.
Yep.
And then the other thing that is bad is the one that Christoph mentioned, right? Where we have x and another x here, right? And technically this one should be bound to this, right? This doesn't exist anymore inside here, right? So when we do this, we should be getting lambda x dot x back, right? But instead we will get lambda x dot y. By the time you fix that problem, your simplifies 2 should compare alpha equivalence. You mean this one? Yeah, possibly. Right? And it was expecting x, but it got xy. Which I think means that we are using these things in a wrong way. Okay, yeah. Okay, so we were expecting xy, but we got xx. More like it. Okay, so I guess since they are in failing test, we could just, for the sake of, we could just annotate here with what we actually get, right? But we know that they're failing because, like, this is how they work, but it's bad that they were like that. Okay, so do we want to do this first, or do we want to do... and I think if we do this, then we'll probably, and like that's all we'll have time to do today.
Let's finish with the substitution problem. So next time we start on logic.
I think we need to just, like, it turns out that we can only do one thing, right, in a stream, so... Okay, so let's see, let's go to, okay, is this a simplifier code? Yeah, this is a simplifier code. I don't think we need these comments anymore because we have a lot of tests which kind of, oh wait, we have this still that we need to do. So what do you think is more interesting?
The
substitution. And then I can do this on my own or something.
On your homework.
Okay, so let's see. What do we do, right? Because one idea was Kaelan's blog post, which Christoph pointed out, which was some combination of both Debugging indices and name variables, so that you have both.
Okay.
So do we want to have a look here and see how to do this? Okay, so I have skinned this.
Maybe you should put the link.
Yes, I should indeed. Okay, so the idea is that we're working with this sort of type, which is very similar to our type, except it's parameterized by a, right? So you can have anything here. It's like as a variable, or like here we have symbol, right? So for us, A is symbol for now.
Okay.
Right, let's keep that in mind. Right, because we use symbol for variables and we use symbol for the lambda head. Okay, so then, here is like just explaining that, we need to evaluate or like to simplify, to do something with lambdas, so we'll skip over this part. It's very good. You should probably read it if you have the time, but right now we're interested in anyway, it's saying that we can simplify this and get back like if we have y here. I think this is literally one of our examples, right?
Exactly.
And then it's saying exactly that one of the problems is alpha renaming in some cases, like the ones we discovered ourselves that are problematic. So in practice, it means in order to compute, we would first need to alpha rename variables. So this example here is you kind of like brute force try to find free variable names, right, and rename them, right, which would be something that probably would be the most naive way that you would do it by hand on paper. I just let me find new names here, and unless it's like a huge term, it's not too hard to find new names, right, and you just rename everything. And it's probably like the easiest, like for example when I did exercises manually, like on paper, I would just read everything and I just I don't care if they would ever clash, I'll just rename everything such that there's no chance for it to clash. Right, that's the simplest way. If you're not like, unless you're doing lambda calculi every day for years, that's probably you should probably do that. So there's a whole host of more sophisticated methods for dealing with the problem of capture avoiding substitution, and one of them is one of the best known ones is the bridging indices, right? So what's the idea here? The idea is that instead of writing this, right, lambda x dot lambda y dot x z, you can like erase all of this.
Erase the names.
Like erase the names in the lambda head. And if whenever you find the variables, you replace them with their relative position, pretty much. So it's kind of like, how deep are we? That's the maximum number you could find here, right? But I think this example, in this example, we're using 1 for the first. I'm not sure why this is 3.
Because it's z, and z doesn't appear, so.
Oh, okay. It's pronounced de Brown. Oh, okay. Okay, thank you. So wait, so if z doesn't appear, why does it get 3? Is that because I don't get this? Anyway.
But what happens with the free variables?
Well, so the idea is that, I guess that's what happens if you use de Brown indices, right? You basically have to rename everything with a number, right? So I guess that if you find something that's not bound, then you have to use the next available integer, right? I guess that's the algorithm. But the approach that Kalin suggests here is that instead of that, let's use, why not both? So it's kind of like if it's a free variable, you keep its original name. Like z or x or whatever, right? In that example, exactly, it's z. But if it's bound, use an integer instead, right? And then also in the lambda head, we keep its name. We only replace it in the body, right? So the equivalent here would be, we keep this and we write 1 here and z here, right? And then we can recover the name by looking in the lambda head, because we don't lose it.
This is what I wanted to ask.
Right?
And then you replace in order to...
But like you can still, even if you see 1 here, you have an algorithm to find the name for 1.
Because as an output you want to...
you want to tell the user, 1 is not type A, is type B, as you... Right? Instead of saying 1, you want to say X is not of type A or whatever, something like that, right? So you want to keep the names as well. So that's the idea, right? So this means that we need, like, our symbol needs to be maybe something like this, right? Symbols could be either strings or a number, right? Which is an index. And then here's the algorithm, which goes from a term using strings, or like in our case it's strings, but this could be anything, right? Some A uses A's for variable names. And here it uses like var a, right, which is var is this thing, right? So it's either a or the integer. And the idea is like this. So let's look at the simple one. Application, you just go recursively left and right. Lambda is okay. So if we have some, we have some fn here, right? Like okay, we have a name here. Like originally, we have a name here, like a string in our case, and an expression, right? So what we do is we annotate it with f, which is like the symbol name. So we keep the original name here, as I said, but in the expression, right, we recursively call our function with the change environment. So what's the environment thing? That's the tricky part. Okay, so we start with empty, which is an empty map, right? So it's a map from a's to integers, right? So we start with an empty map initially, and whenever we find a lambda, we insert the current name as 0, but we +1 everything else. Right, so like the first one will be 0. Yeah, so actually I think this example is wrong, right? Well, it's not wrong. This is not wrong. This is just probably this is how debugging indexes work, and this is probably like you end up with like the lowest number, like 0 will be the closest binder, right? And then the next one,
and x should be 1.
X should be
so
1.
So at the end you get the same, you get 1z, but if you had...
Yeah, but if you had more, then you would get... Okay, this starts from 0 and this starts from 1. That's why, I guess, right? You get the same number there. Right, and then for variables, this is where we actually do something interesting, right? Because until now we're just preparing our state and not like descending left and right, right? But like this is an interesting case where, okay, if we find the variable in our environment, right? So basically what does it mean? If it is bound, right? Then we replace it by its index there, right? Lookup finds a inside the map, right? So this is its index, its number, so we put it in as a variable there. Otherwise we leave it as is because it means that's a free variable, right? That's pretty much everything. And I think all we have to do is just do this, and then we don't have the problem anymore. We can simplify without any
locally.
So this should fix at least one of our problems. So should we implement this? Okay. I'm very happy I did this because I don't know if it looked like I knew what I was saying, but I didn't know what I was saying. I was I kind of also understood as I was explaining. So okay, let's make the simple thing. Let's just replace symbol. Do we agree?
Okay.
Rather than add type variables and so on, because that will make things more complicated, right? So let's say that our symbol instead can be, or we could do the same. Like, should we add an a here instead? And do a different type, or should we just replace the symbol? I think it's just easier to replace the symbol, to be honest. Yeah, let's do that. So let's do data symbol, and then we have, let's keep the same name here, just so we don't have to change a lot of code for like the normal string version. And let's do index int here instead, right? Let's just do this. Then we get, you still need the nameful representation. That's what the parser produces. Yeah, I mean, I'm not sure if you're a bit behind on the code, but I think this will work, right? Because the parser will only produce this. It will never produce this because the parser will not know about this constructor. The parser will just produce this, right? But the trick is I will just store both like this. And I guess later as homework I might make it like add type variables and make it nicer, but for now this will be the fastest thing we can do. So let's do this. Oh, I already had. Okay, so then we need to do where you have a partial. I don't think we have pattern matches for symbols. Maybe I'm wrong. I'll search for that. We'll see if we have a problem there. Show t equals generic show t. I think EQ, Purescript can derive EQ, right? So it's just this one which needs a... Okay, so this works. So let's see in the parser code if we have any problems here. I don't think so, right? Because we're only constructed, we're never pattern matching in the parser. So this works out perfectly fine. And then I think in the tests, again, I don't think we pattern match on anything. We just we just test for equality, right? So if we run our all tests again, I'm pretty sure they will just work. Wait, import. Oh, okay, yeah, some redundant imports in the simplify, right? But all the tests still work. So I'll watch the recording. Today's stream was awesome. Yeah, thank you very much for joining. Okay. So yeah, all our tests work. So
okay,
we can continue, right? Because again, like here, we don't even look at variable, right?
Yeah.
Inside here. But okay, the thing is, before simplifying, now we have to do that trick, right? We need to locally rename, and then we need to simplify. But the thing is, simplify is a recursive function, right? So we kind of need a special step before, because otherwise, like, we'd have to change simplify too much. So let's like, we'll rename simplify. So let's rename simplify to simplify. Like, oops. Okay, I meant to do that. Like simplify prime and just do a simplify like this, right? And then we can say simplify is
locally
to locally named term, right? So we first we do to locally named, then we call simplify like this, and then we need to go back. Right, something like this is what we need to do, and then all we have to do now is implement from and to locally named. Okay, so and these will both have the same signature, right? There will be from s.term to s.term, right? They will all be the same. And I'll just write this so it compiles, right? Right, and then it should compile now. Why doesn't simplify is undefined here? What? Are you serious? The value of simply. Oh, I think the problem is no, but it's even should be. I mean, that's a bug for sure, but okay. I don't think that that's a problem because they are functions. That's weird. Anyway, okay.
Okay, let's do the two locally.
Yeah, let's do two first, right? So I guess I'm pretty sure it will end up being the same kind of idea, right? So pretty sure it will be go empty. Is this from prelude? Yeah. Okay, and then we can do go is a map, data map. Okay, where the so do we? I guess we need to use like from string to end, right? Because we know we use strings for names, right? Okay, and then we go from s.term to s.term, kind of the same thing, right? So okay, go environment, right? And we do pattern matching. So okay, I'd probably write it in the opposite order, in order that we read them, because for me that's the most reasonable, right? So so if we have an application of left and right, then the result is just also an application where we go with the same environment on left and the same environment on right. Yeah, because they're like distinct. It doesn't matter if they repeat, because they're like this. Yeah. Like they cannot clash anyway. Okay, and then I guess abstraction is the next one, right? Because this is when you set the things up to then using variables, right? So you have an abstraction with a symbol and okay, see, this is where it gets slightly awkward if we do this, but that is not too complicated, too bad. Okay, and some term, right? So here we kind of need to look at symbol, right? Because what if symbol is already an integer, which it shouldn't be, right? So we should probably error in that case. Or I guess in that case we just don't change anything, but it's pretty weird. We might want to actually throw an exception or something. Should we? I think we should throw an exception in that case. Right, so like two locally names would assume that they're not yet locally named, right? So we should throw an exception in that case. So let's see. Let's just pattern match here, so it's even clearer. So if this is a index is what we call it, right? Then unsave crash. Term, right? And then symbol. Where can we do just this? Okay. So the idea is we need to also return abstraction, right? With the same symbol, right? We need to. That's fine. And then the inner term needs to do go, right? Like need to recursively call go with an updated map on the inner term, right? And this is the trick here, right? What we do here. And what we do here is we do m.insert, which is the map insert, which is this one. So we insert, so I guess key goes first, if I remember correctly. So yeah, it's key. So key is 0, value is var, right? The variable name over m.map. There's no map. Why is there no m.map? Is it unsafe map or like some special name for map? I think it has to. What? Oh right, because values. If map is a functor. I was thinking about set. Set cannot be a functor, but map is. So we do +1 over environment. Right?
You do the parsing first and then you do the simplification, right?
You do the parsing first. Yeah. And I wrote mapty here. Okay. So insert 0. Okay, it's the other way around. Insert variable 0 because the numbers are on the right hand side. Okay, now the problem is that you're not telling me how to simplify the rest of things, but then like left simplifies to left and tuple simplifies to tuple because they're just units, right? We don't care about them. They can never do anything interesting. So I think that's it for this part, and now we need to go the other way around, right? So you need to do from locally named. Should we test this separately first? Where is it? Simplifier test. So do you want to test it in the context of simplify or just call it separately as a function?
What do you think?
Separately, I guess.
Okay.
So let's do like 2 locally named tests. Okay, so what do we want to do here? Well, we want to...
Let's take that example with...
Okay, so we want to do something similar to simplifies 2, right? So let me copy simplifies 2. But then locally names 2. Right? And then we also do parser, but instead of simplify, we do locally rename. No, to locally named, sorry. Okay, so we want to do which example? So even like, I mean, even x, this is the simplest thing, right? And it should be 0 x, right? No, x is 0.
Yeah.
Like this. Wait, to locally named. Oh, okay. You know what? We know what the problem is. This is not valid in for our parser. So we cannot use our parser for this.
Yeah, that's why I was wondering.
That's what you were asking? Yeah. I misunderstood your question.
Well, it wasn't asked properly, but I was thinking of this. If
yeah, this will not parse.
But okay, don't use the parser. Just write it as you were writing. Yeah.
Yeah, but then this kind of isn't as, because if you're going to write term here, yeah, I know, but I guess t, right? And then we need t off here, and then if the term is correct, then it should be equal what? T with locally named. Oh, it's the same thing, so as expected here. Okay, and then this needs to okay, and there's no more. Okay, and then this is a problem, and this should be something like abstraction of x, yes, and then we can do var 0 because var is just a silly constructor, so it should work. Expected xx, but got so I got the wrong order here, but it's not doing it correctly apparently, right? Because we were getting xx.
Can you say it again?
Let me save and run it again just to make sure. Yeah, so expected x 0. But so anyway, it's not symbol. It should be the other constructor. But anyway, it got xx, so it's still wrong. So the code is wrong somewhere. Okay, so if we have an abstraction. Oh, okay, I know what the problem is. Oh no, I don't know what the problem is. Okay, so if we have an abstraction like this one, then we construct an abstraction where we use symbol here, and then we go with inserted variable and you know what the problem is?
Variable,
yeah, exactly.
Right?
We didn't write the variable case. Yeah. we built the map, but we didn't do anything with it.
Search for the variable.
So okay, if we find an s dot.
Okay, I will take a 5-minute break.
Okay. So if we have an s dot variable of s dot symbol variable name, in that case we need to look it up, right? So case m dot lookup. So we're looking up the name, right? Yeah. So if we find nothing, then we keep the same thing. Just return v, and if we find some number n, then or some index I, then the result should be s dot variable of s dot index I instead. Need to import this constructor. Alright, and we need to look it in the environment, of course. Okay, so now I think it should work. Ooh. Oh, okay, so now all of our... Okay, so now our other tests fail because we don't rename them back, right? So for example, we're expecting to get symbol x variable index 0, what we got like symbol x variable symbol x, right? So we need to go back and rename them, right? So we need to write the other function, but this test succeeds, right? So I think I want to fix that first. So I want to do from locally named now in order to fix things. And also this is, again, so this fails because this needs to be index. So instead of symbol, or not instead, but next to symbol, let's have I index, where this is s.index. And actually it should take a number instead. So let's do like this. Hello. So why is it a term?
What happened?
Okay, so we need a term actually. So it's okay. So okay, it worked, but our other tests failed because we don't rename back, right? We're expecting to find xx, but we're finding x0, for example, right? So we need to fix those, right? So for example, we're
let's implement the other one.
So let's implement the reverse, right? Because like this one passed, right? The test that we wrote, like the simple one.
Can we try an example also with free variables?
Here?
Yeah.
So like just xy and just to make sure we get back xy?
Yeah.
Like so? Okay. It surely works. Yeah, it works.
Yeah.
Okay.
Okay.
Let me just add something there. Okay. So, I mean, let's look at the algorithm, right? Rather than trying to guess it. So from, okay, it does pretty much the same thing, right? Still a map. Okay, so knowing that, let's see if we can figure it out without reading. Okay. I mean, this should be pretty much the same thing, right? Okay. If an abstraction of s.index, right, and some index I, and a term. Well, no, we should never have index here. That's actually an error, right? We should always have symbol here.
Yeah.
So this, like, if we have index here, then we actually cannot recover the name, and we will error because that should never happen.
Yeah.
Okay, so if we have a symbol here,
write
then
var as you wrote in the other case.
Oh, what?
Put the same. You have a symbol var.
Oh, okay, sure. I was thinking about index, and that's why we had an I there. Okay. Then I guess we do this. Well, okay, sure. We do abstraction. We leave this as it is, right? Here, but then we need to change the term, right?
Yeah,
so we need to go. Is it the same thing?
No, you use the same environment. You never modify now the environment, right?
But you don't have the environment anymore. You have to build it again.
Ah, sorry.
You have to rebuild it every time, right? But the information is here in the head, right?
Ah, sorry, yeah.
So like you don't keep this. We could have kept it, but
okay,
we don't.
Sorry, I see. Okay, yeah.
So we do have to insert, but I think it's literally the same thing, right? I insert it here, and then it +1. I think it's literally the same in like algorithm. But then the only difference is what you do in the variable case. I'm pretty sure. Right, because, okay, so if we find a symbol, then we do nothing, right? So only in case of this, right? In symbol, we just fall back to this, right? Where we don't do anything. So if we find an index, then we look it up, right? Well, this is an I, right?
Yeah. Look up.
Let me think for a second, because we cannot look up I's here. We need to do the other way around. Is this map opposite? Yeah, right? You see, the map is reversed here. Because you need to look up the other side, right? So you need to do 0 and var here. And here you need to like map the keys, I guess. Is there a map? Is there a map key here? Yeah, map key is monotonic, right? So I need to find if there's a function like that here. And we really hope there is. From to delete pop member alter keys filter map no. I mean, wait, and this changes the value anyway. No. Whoops. We don't have a function to map keys. Well, we can write it and it will be slow, but we don't care about that, right?
Yeah.
Okay, so let's write the function before continuing here. So map keys, keys. Okay, so if you give me a function from k to k1 and a map k a, I can give you back a map k1a, right? F, right? And then we we go to like m dot to to unfoldable. Yeah. I guess we should do array dot to unfoldable. Okay, and then we get like an array of tuples. And then we need to map over like map a map. So this is okay, so this is inside the array, this is inside of the tuple, but we need to map the left hand side of the tuple, so it's lmap, yeah, of f here, and then it's m dot from foldable. I think that's correct. Looks like it's correct. Okay, so here we need okay, so insert 0 because we need the numbers, right?
Okay.
And the variable name, and then we do map keys +1 over environment. Okay. Okay, and now we need to look up I.
Yeah.
Right, the index. Let's do IDX instead. Right, so if we don't find it, it should kind of be an error, right?
Right.
Sort of, right? Like bad index in locally named term, I guess, right? Okay, and then if we find like the variable here, right? Then it's symbol this, right?
Yeah.
Could not match map k0 with array. Say one now. Okay, so array to unfoldable. Oh wait, from. Isn't that the thing? Okay, but then how does it know I wanted to use array? Okay, so we need ord k1, sure. And then not type class found for foldable. Foldable t3. Oh, because it exactly doesn't know which function we're using here. I thought. So how do I do this? Can I instead use array.map? Is there such a thing? I mean, I just need to annotate something here, I think, and that will work. What's the easiest thing to annotate? It's a function for all b c b goes to c r. Okay. Kind of like it doesn't have the type information. In Purescript we don't have type applications, right? Because it, like in Haskell I could have said this, right, and apply it to array. But since Purescript doesn't have that, you kind of have to annotate somewhere. Map keys could not match. I think we also need to replace this, right? Okay, cool. I'm not sure if there's like, if anybody knows in chat if there's a nicer way to, like a simpler way to do it that I'm not seeing right now, let me know. But I'm not seeing the simpler version right now. Okay. So now it should just, all our other examples should work. Bad index in locally named term. Okay, so we have one problem in locally named term. Okay, and this is why it's not cool to have unsafe crashes. Yes. So I guess in one of these examples we, this one.
No, the other one. The other one, because...
This one?
Yeah.
Nope.
Wait, let's look. Okay, let's try to see, let's do locally renames to that term. Lambda x, lambda y.
Wait, no, I want to see which one is the problem. So let's see. So it passes the simplifier variables and abstractions. So it kind of gets here and has a problem, I guess, since it doesn't type application. Or maybe it's just here. No, it can't be here, right? There's no way it's here. So that means it's this one, the first one, or somewhere in here. So let's see if we like comment this out. Does it work? Still no. I kind of want to write something, but what would I even write? Should we? Oh, you know what we could do? Okay, we could do something that's, so this is the original term, then write it here as well. But we could just write the original term here rather than the subterm, because here we only have access to a subterm, but this is the like full term. So you could maybe print it here, right? That would help us at least. In like this, right? But I think this was the error, but let's add. Okay. So let's see which one was the one that crashes. Variable index 0. So that's the whole term.
What? But are you sure it is the same?
Wait, I think we.
I
think something is wrong.
Yeah, I think you're from locally named. I think.
So wait. Okay, let's do something else. Let's do this. Is that the first test that's failing? I don't think so. Right. Okay, so this works. Okay, does this work? This should do no simplification, so it should not fail. Okay, so this works. There's this one which fails, I guess. Okay. So we should be renaming X, but not Y. It should be 1, 1, or 0, 0, and replace Y. 0 with Y. Oh, wait. Because, okay, so yeah, we have a problem. So wait, we have symbol here. Oh yeah, but wait, but this is like, this is a, so they should still be equal, right? That's all we care about. Like if we're trying to replace 1 with 1, then that's, oh no, it's not good. It's not good because we're using the head part. It changes our simplification algorithm. Oh, how do you even do simplification now? Or wait. Because like,
wait.
Yeah, it has to change, right? Because we can no longer look for, because right now we're looking for.
But you shouldn't, I think you shouldn't do it in the simplification, you should do it in the substitution. I mean, leave the simplification as it is, but then when you want to substitute, first rename.
Oh.
Then substitute and then rename it back. Don't do it in the simplification.
Oh, I see. I see what you mean.
So I think it's like what you did for simplify, just do it for substitution.
So we should do that for left, right? Left is the thing that we should.
Yeah, I'm saying just rename your substitute function with.
I don't think we need that. I think we can just. Oh, okay. You mean just instead of doing it here, let's do it here. Okay. From locally named. Well, wait. It should be the other way around. Locally named. What do we want to locally name? The term, right? So this needs to be. Okay, let me do something else. Okay, in.
Yeah.
Like this.
Variable whoisty.
I don't know.
Term prime, not T.
Like this.
And then you have to, yeah. Okay, try.
And let's actually go back to this one, right? Like substitute should be, like simplify, sorry, should be their simple simplify, right? Without. And let's move these two at the bottom because like the first thing we should see is simplify. And these are like implementation details for substitutes. Okay. So does this work now?
Yay!
Okay. Good job. Good idea. So let's be brave. Yeah. Brilliant. Okay, so let's actually see if we fixed any of the problems we were, because right now we just unbroke what we broke, right? So let's see if we actually fixed any of the.
Okay, but wait, let's look at the examples because
I know one of them is not fixed. I want to see if at least one is fixed. Okay, so only one failed, which is the what? We have no idea which one failed.
Wait.
So X.
So what we want to get there? We want.
I think we fixed. Wait, no, okay, no, here, this one. Okay, I was looking down there, these ones. I think we fixed the second one. Oh, no, we fixed the other one.
Yeah.
Okay, let's make sure that that's true. Okay, why? So
because
okay,
yeah.
I was reading it wrong. Okay, so here we just put y here, but then this but then this still simplifies to y. So we didn't fix anything, because this wasn't the one we should be fixing. So this should simplify to something else, and this should be alpha renamed.
We did not fix anything.
And then what's this problem? Here, so it should be xy. Okay, like this should have been fixed actually, right? Because like this should turn like this should be 1 2 or 0 1 1, right? Or rather, okay, let me use the correct things here. So this should be 0. Well,
no,
it should be x
1.
X, and then this should be 1, right?
Okay.
With our alpha, like with our locally named thing, right? And then we should replace it, like we should add y here, right? Apply y here. The result should be x 1 with 0.
Why?
Okay, it should be x1, but then this one needs to become y. No. It needs to become. Wait, what does it become?
See the problem. It should become 0.
No, it should be x. Okay, yeah, it should be 0, and then it should be.
Yeah, but the problem is that you have.
Sorry, x.
Yeah, but the problem is I think it remains x1.
1, right? Is that what the test is telling us? Let's run it again. So are we getting 1? Bad index variable. Oh,
yeah.
What do you mean? But like, the term is index 0, which is correct.
Where do you get? Can you go back where you throw that extraction?
Oh, okay, never mind, because I wrote it wrong. This should be written as, this should be 0, remember? Because like this is 0, and then this becomes 1, and this is 0. Like we count from inside to out, right? So inside is 0, and outside is like 1, 2, layered. So it's looking for, right? So we know that x is 1, but we don't know what 0 is, because Oh. Okay, let me think. But wait. Okay, so when we actually do the right, so I think somewhere to locally named.
But what happened?
So what happens with insert? Because like we go in. Okay, so we end up giving x the value 0, right? Which is correct, right? We override it, right? Because that's the idea, right? Because we have a map from string to ends. So like the inner x will override the outer x, right? Because we start from the outside and we go inside, right? And like the old x, like they get incremented like for every step, but then it gets overridden because it's the same name. Okay. So this at the end, the environment is correct, and we have 0 there, right? Because we have 0 there. We know we have 0. So then this is correct, but this is not correct, right? The from locally named. So
you got a bad index in locally named term.
Okay, because we are looking for index
0.
Wait. But why are we looking for? Okay, so no, I think we're looking for index 1. But why are we looking for index 1? Okay, let's also show the index here. Something like this. Like what index are we looking? I think we're looking for 1. No. We're looking for 0 and we're not finding it. Okay, let's look at the, so what do we have in our environment then? So, okay, what's the result? Result is an abstract.
Can we have a look at his algorithm?
Like the from locally named?
Yeah.
So if we find the name, we do that. If we don't find it, then okay. So then here is the thing, right? I mean, it's the same, isn't it? We didn't get this, right? So it doesn't matter. So we have a symbol, then we insert 0 and then +1 on the environment. Over this term. Yeah. Okay. Does map have a show instance?
Wait, can you go back?
Yeah, it does.
Can you go back a bit to his algorithm? Okay.
Oh, sorry. Yeah, it's fine. I want to see what's inside our environment then. Oh, so our environment is empty. Why is our environment empty?
But I'm afraid it will never enter into, because you'll not have the symbol var now anymore, right? Or wait. So now we did the simplification. Go back. Where are we using this?
I think I know what the problem is. I think we need to. I think what we had previously. So why did we end up not doing from locally named into locally named at top level? What was the problem in that case?
The simplifications?
Yeah. Why did we change it?
Because the tests were failing?
Because the problem is you don't have enough info. Like this is a local substitution, right?
You have to do your homework.
It looks like it.
We have to go.
Yeah. Okay, I mean you have to go, I guess, right? So should I stop?
Yeah, I think we have to think carefully about when we do the renaming.
Mm-hmm. Yeah.
So I think that's the problem. I still think you have to do it
locally.
Yeah.
Yeah, I'm not sure. I need to think about it for a bit.
Yeah.
So should I not work on this, and do you want us to work together next time, or do you want me to figure it out?
You should figure out and do.
So you can do logic next time.
Yeah.
Okay.
Let's do logic.
Finally do some logic. Okay.
Logic.
And I'll probably do some other.
But we should. I mean, maybe we can start with this next time and see what was the problem.
Mm-hmm. Yeah. Like today, right? Because we went over the parser, and next time we'll go over this and see how I fixed it, and then we can finally get to the logic part.
We start with second calculus.
Okay. Then I'll take a few minutes break, and then I think I'll work for another 10-15 minutes on this, and then I'll shut off the stream. Okay. Then let's do a quick break.
Bye.
Let me put on some music.
as I watch the weather change. The clouds collide on either side as nations rearrange. A silver mane adorns me, my steel is fluid and fast. They shun my ways, avoid my gaze, a fugitive outcast. There is no pain I can feel. True retribution I deal through silver and steel. Silver and steel. Deadly dark elixirs, caustic curdle sour. Wound and weave and carve and cleave, engulf my guts in power. By tome or trial I master the secrets of the beast. By trap or burst now be dispersed, from torment be released. There is no pain I can feel. True retribution I deal through silver and steel. Silver and steel. Better make way when the Witcher comes. Lebro is done. Better make way when the Witcher comes.
Okay, and I'm back. Let me reclaim some of the space here. Okay, so what's actually going on here? I think the problem might be in substitute. Oh wait, we're still doing this. Okay. Okay, so that might be one of the problems. Oops. Okay. Okay. Well, that was easy. Okay, so now this thing works correctly. So I think this still cannot work correctly. Oh. Okay. Never mind. Oh wait, no. So let's see. Neither is any of this correct? So they're still wrong. What? Wait, give me a second. So substitute. Wait, no, I did the wrong thing. This definitely needs to be here. And then simplifies. Okay, never mind. I'm crazy. That was not the problem. So in this case, what do we expect to happen? We expect the result to be... Well, okay, so this I don't think we can fix without alpha renaming. And this should result in lambda xx. Oh, okay, see what the problem is. So should we do it here? So the thing is, I don't quite remember why we end up doing this. Why we ended up doing this. So I will actually undo this, and do this, and go back to doing it here. Is it possible to do property-based testing of a lambda calculus with quick check? Yeah, it is. We'll just have to write a generator for terms, and I think this article actually does that here. So where is it? Here, right? He wrote an arbitrary instance, like Cahill wrote an arbitrary instance, right? And he built terms. So I guess here is like, if like from 0 to 2 inclusively, you just create a variable. From 3 to 8, you'd create a lambda, and otherwise you create. So this is just like a 20% are, or is it 20%? Yeah, 20%, 60%, 20% or something, right? Variables, lambda, calcula, abstraction application. Let me link you. Let me post the link. Yeah, this is one way, but again, you definitely can. The question is, yeah. But I think this is a. Okay, so you build term. Yeah, can definitely build terms like that. So let's see. Okay, right, so I was going to do this version, right, where we do from locally named simplified to locally named, and then this should be, oh, let's do the other way around. Okay. And here we need this and this. Okay. So what happens now? Okay, so it's the same problem. Okay, so what happened? Let's go step by step here with our example. So let's see, we have this thing, right? So it goes to application first. Okay, so what does our thing look like initially, right? So it's lambda x dot lambda x dot x. And then we want to apply a y to it, right? So then this gets renamed to lambda x dot so this would be 0, right? And then y when we do this thing, right? So we get here, we get okay, we write all of that, and we want to substitute the variable x inside this thing. Okay, and we end up not needing to do that, right? Okay, and then we end up with what? This. We end up with this then. We actually don't even need these parentheses. Okay, so we end up with this. Alright, so then why can't we do from locally named with this? From locally named. Shouldn't we have an abstraction with a symbol there? Like, isn't that what we're building here? Wait, why are we... Okay, no, this is fine. Okay. Okay, so I want to add a different test then. I want to add, well, I'll just add it here. Okay. Okay, so if we have something like this, I wanted to say that it's this at the end, right? So we need to do the same thing but reversed, like this but reversed. Okay, so it's what's it called? From locally to. Okay, and then it's the other way around, right? It's a okay, and then it's this. Okay, so it should equal x with, I think that should be the right test to write, enable to what? Okay, because there's nothing here. Okay, let's do this. Okay, and then let's add the test here. Oh, well, no, we don't need that. We already have it added. Okay, so let's run the test again. Well, it crashes on that one. So let me comment this. What? Wait. Wait, which test is failing now? Abstraction. Oh, so it's like normal tests are failing now? Okay, so expected x but got x and index 0. Okay, so from locally named. So wait, we have an abstraction with a so we got an abstraction with a variable with an index. Okay, what if we have an abstraction? So if we have an abstraction with a symbol, right? And we get back an abstraction with the same symbol, but then we go, okay. And then we put that variable as 0. And then we go further inside the term. Yeah. Okay. So why am I not getting the exception then? Because then it should get here, right, with the term. Like it should recurse get here, because like the result isn't. Oh no, okay, no, it's getting this. Okay, let me have another look at the test. Did I write the test wrong? So this expression and this is the input. So I'm saying that the expression, so I should do from locally nameless expression, and it should be equal to t. I think that's the problem. Okay. Okay, and then it does pass. Okay, but then it's more confusing now. Okay, so then let's see that this doesn't work now. Bad index in local index. Okay. Lambda x dot x y, and the result should be y. Yep. So let's see. What's our code for substitute? So it doesn't do any normalization inside substitute, which is what we want. Okay, so we applied normalization here, right? So every term should be normalized, and the result should be like lambda. Okay, so let's take the simpler example, right? So the result should be lambda. Oh, okay, so we start with lambda x dot x y, and then this should be normalized to lambda x dot 0 y. Welcome back. Not very good. So lambda, so this needs to be like, this needs to just become y, right? So why is it why do we have a variable with index 0 at the end in our test? Right, it's this test, right, for sure. That's the biggest I've told you so moment I've had in a few weeks. The one where I said that it's going to be easy, and it wasn't. Okay. Well, that error is a partial part. Yeah, I know. I think it's actually like it's bad index. If you had for named and locally nameless or parameterized like the blog post. I'm not sure. So we're hitting this bad index. So we have a variable with an index and and we cannot find the index. Why? Like we should do from locally named only after we've substituted, so there should be no index. And the term is okay. Now I know what the problem is. Okay, I know what the problem is. So the problem is we've done these like locally named part, but where is substitution? But substitution does this, right? Subtract as you go down. So I think the problem right now, I'm pretty sure that's how the algorithm is here, and it seems to be working here. Like it's doing +1 either way, in both from and to locally. And I think that should also work the same. But the actual problem is here is in, so when we're doing simplification, right? When we're doing application and we have application of an abstraction on the left hand side, here it's a variable name, right? So here is X. And that's what we're passing to substitute. But here we're like the replacement only happens here, which is wrong, right? Like we need substitution to be aware of indexes somehow, or we need to like fix it somehow. And I'm not sure how this works, right? Because now we have things that are unique. Yeah, that variable name is meaningless until we go back to the original name. It's just we can recover the original names. Yeah. So the question is, how do I go from variable to name here when we're doing simplify to index, right? The blog post describes open. Okay, so what's open? So open is what? Oh, is open just substitute? Okay. So what does substitute do? But you always substitute the index 0. Oh, okay. I mean, that makes sense. Okay. I'll give it a few more minutes, but I have to go after that. So let me try to implement this thing then. So let's see. So open is what? I guess we only need 2 terms. Okay. And we have what? We have like a term and replacement, and we say go 0 and term, I guess, right? Okay, so what's the interesting case here? I guess the least interesting is this. We have an application of left and right, and we just do we +1 on application? I don't think so, right? That's just like a number for wait, not 0, it's outer. Okay. Oh no, it's abstraction, and then we don't care about this, right? Because this is literally useless to us. Well, I guess we need to recreate it, so it's like first variable name or like symbol and term. We need to keep the abstraction, but then go outer +1. Okay. and then if we have a variable, what happens in the case of the variable? So if we have a variable name, then we don't do anything, right? Oops. Does this work like this, or do I need to parenthesize? Okay, so if we have an index, we just check if it's I don't get this. So why do we compare with outer? Oh, I see. Because then it increases. Okay, yeah. So then we return replacement, and otherwise we just return the initial thing, right? Okay. I guess this needs to be parenthesized. Okay, and then in all other cases we don't have any recursiveness or anything interesting, so just return the initial term. Well, okay, so we need to do open instead of substitute, I guess. Okay. Cool. So then to our other tests pass, like these ones, they should, right? Oh, what did I break? Oh, okay. Okay. Cool, so now we're back to where we were before we started trying to fix this. Okay, so should this be fixed? No, this should be fixed, I think. Cool. I think this isn't yet fixed because we don't look at that problem yet. Oh, wait, what? Okay, yeah, but this is correct. This is wrong, right? It should be something else here, right? It should be like some... this is where you said that we need some alpha equivalence thing here, right? So I think you will get back y.y, but... well, we didn't write any info here. They're just not equal. Wait, no, it's not parsing. Oh, right. Whatever. Right, so we got y.y, which is wrong. You wouldn't know it's wrong if we applied this to something else, I think. Yeah. Maybe. Yeah, I don't think you could observe that this is wrong if you apply this to something, right? Because if we applied this to like x, then we would get x instead of y. Okay, let me write a different test, because this is a correct test, right? So if we take all of this, because the result is y.y, right? So if I apply this to x, we'll actually get y instead of x, I'm pretty sure. So like the problem is just when we are from locally named, when you're going back, we need to make sure that we're not renaming back if the clash happens, I think. Expected y got abstraction ay. What? Oh, here. Okay, yeah. But like this one is actually, this is correct, but this showcases a problem. Yeah. Okay, cool. I need to go now. But yeah, thank you very much for watching, and thank you very much, Krista, for helping, and I'll see you guys tomorrow. Bye bye.